Hello guys, so today I'll be starting with fluid mechanics. So, fluid mechanics, first module we will be going with fluid statics. So basically fluid static means that when the fluid is at rest and not moving, it obeys certain properties. These properties we'll be studying in detail like viscosity, specific gravity, and lot more. So we can go for equation viscosity. Now we can go to the topic which is viscosity. Viscosity is a phenomenon which occurs due to internal friction. Internal friction force that develops between the layers of fluid. I'll be explaining this in detail. So let us assume we have a pipe here. Okay. So there is some water, something is flowing, a fluid is flowing through this. Now assume that here there are different layers of fluid. So there should be any friction, a friction force between these layers. This friction force is known as viscosity. Water has very less viscosity, while honey has more viscosity. In general, viscosity is a force which opposes the flow of a fluid. It's that simple. So, water can flow very easily, while honey takes a little bit more time to flow into something else. Like we can pour water inside a cup faster than we can pour honey inside a cup, right? So that is because of the action of viscosity. Hope that's clear. Now, there are two types of viscosity. Uh, no, sorry, dynamic viscosity and kinematic viscosity. So there are two types of viscosity, dynamic viscosity and kinetic viscosity. We have formulas for those as well. So the dynamic viscosity mu is given by tau by dou u by, sorry, du by dy. So I'll be explaining all these terms, and this is like tau is our shear stress, du is velocity, and dy is distance. Just keep in mind that this is just a ratio, not can also be a differentiation. But if the distance and velocity is given, take du as the velocity and dy as the distance. Hope that's clear. So this formula can be rewritten as shear stress is equal to mu into du by dy, right? So this is our first formula. Now, what about kinematic viscosity? Kinematic viscosity is just the ratio between dynamic viscosity and density. So it is just mu by rho. That is given by this. So kinematic viscosity is just mu by rho. Hope that's clear. So probably we should be doing some questions, but I'll take a little bit more and start with the questions then. So kinematic viscosity. So now we can go for surface tension. Surface tension is the tendency of a liquid surface to shrink to the minimum area possible. So, assuming like there is a liquid here, the liquid's surface property, which makes it shrink to the minimum area possible. So, surface tension's tensile force can be written as mm, stress into pi d, while pressure force is written as pressure into pi by 4 into d square. So what is another thing is capillarity. Capillarity is the tendency of rise or fall of a liquid surface in a smaller tube. So basically there is a liquid inside this tube and you insert a smaller tube in this, then there will probably be a rise of liquid here. Or maybe any other fluid if you are using, there could be a fall. This place would be empty, the place where this is inserted. So these phenomena is known as capillarity. Hope that's clear. Now we can start with some questions. These are just basic terms. I'll come again after I do questions on viscosity. So let us assume that a plate 0.025 millimeter away from a fixed plate. I'll So this is the question right here. So to answer this question, what we do is we first, whatever question is, first draw the diagram. So it is like a plate which is, so there's one fixed plate and one moving plate, maybe. Okay. So plate 0.025 millimeter away from the fixed plate. So it is 0.025 millimeter. Moves at a velocity of 80 centimeter per second, which is equal to 800 millimeter per second, right? So requires a force of 4 Newton per unit area. So we are taking this as millimeter. So 4 Newton per meter square. Since unit area is given, it's meter square always. So we will be converting this 4 Newton per meter square into 4 Newton into 10 power minus 6 millimeter square. Per So 4 into 10 power minus 6 Newton per millimeter square. That's it, right? So now we have all the. So what we have is dy, which is 0.025, du, which is 800 millimeter per second, and we also have tau, which is 4 into 10 power minus 6. So we actually have everything. We have to find mu, which is equal to tau by du by dy. We have to first find this, then. So what we have is 4 into 10 to the power minus 6 divided by 0.025 by 800. So that will give our viscosity mu as 1.25 into 10 to the power minus 4 Newton second per meter square, right? So that's it. So, okay, guys, so continuing yesterday's class, we'll be now starting with surface tension. I had mentioned what surface tension is briefly in the previous lecture. So, surface tension is defined as a tensile force acting on the surface of the liquid. So, it's a tensile force acting on the surface of the liquid. Okay. So, there is a formula for surface tension which can be written as psi into pi d. So what is this pi d? So surface tension is basically there is this water surface and the droplets above the water. It's like it will contract to the smallest area possible, which can retain the liquid. Okay, that's why. Um, okay, so uh, this is the we'll be getting the surface circumference into its stress. Psi is stress. So that is the formula. And if you want to find the pressure, pressure is given by psi into pi d, which is surface tension divided by pi by 4 d square. So we can cancel quite a few. So it will become 4 psi by d. So pressure on the liquid, what is this? So this whatever the pressure on the liquid is equal to 4 psi by d. Hope that's clear now. So that's it for surface tension. Now we'll be coming to capillarity. So capillarity, I had mentioned this also earlier. It's basically like the water going up of this or any other liquid which is coming down due to an insertion of a smaller area. So it's like a defined as a phenomenon of rise or fall of a liquid surface in a small tube related to adjacent general level of liquid. So there is a formula for this, which is the height. So when we have this let us assume this is the height of rise or that is the height of fall. So h is equal to pi psi into pi d, which is our surface tension into cos theta divided by pi by 4 d square, which is the area into rho into g. So we can cancel out quite a bit here and we get to the conclusion 4 psi cos theta divided by rho g d. So here the theta is the angle of contact between liquid and glass tube. So like when the water is rising in this tube, okay, there it won't be straight like this. It could be straight if it is a liquid. It could also be like this. You are getting my point, right? So this means this is the angle of contact, like that. That's what I mean by theta. So height is equal to 4 psi cos theta divided by rho GD. Hope you got this. This is quite an important formula. So now we have taken that away. We can finally come to our next topic, which is really important. That is manometers. Second. So let's come back to our topic, which is manometers. So what are manometers? Manometer, like there are different types of manometers as well. Simple uh, manometers, YouTube manometers, and of course we got our the next one, which is single. No, that not small. Okay, so as a manometer, only this much. YouTube and simple manometers. So what's a manometer? Like they manometers are usually used to measure pressure. Okay, so let's assume there is some liquid here. Okay, which has risen up to this level, and here there is atmospheric pressure. So we have the height of rise. Let this be the point of our axis. So I forgot that what we call this line. So whatever it is, let this be the height of rise. So that will be given as h. So simple manometer consists of a glass tube having one of its ends connected to a point where pressure is to be measured and other end remains open to atmosphere. Okay. So simple manometer and YouTube manometer. We only have problems regarding YouTube manometer where this is our first chamber, okay, and it is bent like an YouTube. Hope you are getting it. I'll draw the diagram a bit more clearly. So it is like a circle here, okay, and it's bent like a shape. Sorry, it's bent like an YouTube, okay. I'm really sorry about my bad drawing skills. Um, so Let us assume um, these are not liquid actually. So let us assume that mm, this is our data. Yeah, that line, this line is known as data. Okay, common point. So what we know is pressure at these heights will be same. Okay, so if pressure here is equal to pressure here, that is what Pascal's law states. Okay, so I will come to that on later stage, but this is what is it is. So assuming the liquid is like there is a one liquid here which is like let's assume that's liquid B, and there will be another liquid A which will do the rise and fall. Okay, so the liquid A will be like this. So we know that here there is atmospheric pressure, and here there is pressure due to liquid or fluid B. Okay, this fluid will act a pressure will act on this due to this fluid, and a pressure will act on this same liquid due to atmospheric pressure. Okay, so this is one. Okay, this type of this one is known as gauge pressure. There's another one for vacuum pressure, which I'll come in a few seconds. So this is gauge pressure. So for calculating gauge pressure, it's like quite simple actually. Pressure is equal to rho 2 G H2 minus rho 1 G H1. So what are these rho 2, rho 1? So assuming that this red color is the heavy liquid and green color is the light liquid. Okay, so rho 2 is the density of heavier liquid, while rho 1 is the density of lighter liquid. Hg same, H1 and H2 is the height. So this one will be H1 and this height from the datum line will be H2. Hope you got that. H1 means H1 is not this actually, it's still this much. Okay. So H1 is basically like this is a center point. So from this line, H2 minus the distance is the H1. Okay. Hope you got that. So if it is, I will solve a question which will make things more clear for you. So let's go for the question. Here, there is this YouTube manometer. There is this YouTube manometer. Okay. So my drawings are kind of bad. I don't know. Like this pen is kind of tough to use. I'll make it automatic shapes. Okay. So let us assume this is the YouTube manometer and there is a liquid like this. Okay, just assume. So this is our datum line. I will make it with another color. So this is our datum line. Okay, and this height, that height is 20 centimeter, and this is our center line of point of center, and this distance is 12 centimeter. Okay, so we have to find pressure given that specific gravity of the fluid in the left limb. Specific gravity in the left limb is what? 0.9. So we'll be solving this question. So let's just take down what all is given. Okay. Specific gravity of this lighter liquid is 0.9. And this heavier liquid is mercury. So specific gravity of heavier liquid, mercury, is 13.6. That is to be noted because it won't be given usually. And we have all this info. So H2 is 20 centimeter and H1 is 20 minus 12, which is 8 centimeter. Because H1 is this distance, okay? This is H1. So we have that now. So how do you calculate density from specific gravity? Okay, specific gravity is basically like specific weight of water. No, actually specific weight of the given liquid by specific weight of water. So 0.9 is equal to x, which is the density by density of water, that is 1000. So 0.9 into 1000 will give you the density of the X liquid, whatever it is. So 0.9 into 1000 means it's like 900. Okay. So our density rho 1 is 900 and rho 2 is 13,600. So we have rho 1, rho 2, H1, H2. So what do we want now? Just G. G is what? 9.81 meter per second. So we have all these. H1, H2 is what? 20 into 10 power minus 2 meters. This will be 8 into 10 power minus 2 meters. So we have converted everything now. So we can just solve. So our pressure is equal to rho 2 GH2 minus rho 2 GH1. So our rho 1 GH1. Okay. So our rho 2 is 13,600 into 9.81 into our H2 is 20 into 10 power minus 2 meters minus rho 1 is 900 into 9.81 into H1 is 8 into 10 power minus 2 meters, right? So we have all this now. So what is common? So they'll just do this with a calculator. Implies 13. Wait a second. Okay, so that will make mm, pressure is equal to 25,000. No, wait. 977 Newton per meter square. So we can just make this Newton per centimeter. So that will be 2.5977 Newton per centimeter square. Because our heights are given in centimeters, we just have to make them centimeters. So this is our pressure. Okay. So hope you guys got this formula. P is equal to, okay. Hope you guys got that. Now let's get to the vacuum pressure formula. I told you, right? There are two formulas. Vacuum pressure formula. It's like a little bit different. P is equal to minus rho 2 H2G plus rho 1 H1G. So what is this vacuum pressure basically? So we do draw the same manometer, though this automatic shapes are getting annoying. So we basically draw this manometer, okay? Now, what's a different is here, this pressure of this liquid or fluid, whatever, is less than the atmospheric pressure. So our datum line is this. Let us assume. So this is the only rise. Like the liquid rises in the opposite direction. We're getting it, right? So that means our H2 is this one. I'll just zoom in a little bit so that I can give a clear cut idea. So our H2 is this one, while our H1 is this. We're getting it, right? So this is our H1, this is our, the shaded part till the datum line is our H2. The difference between this liquid, height of this liquid from the center line is H1. I hope you got it. This is H2, this is H1. And the formula goes like this. So pressure is equal to minus rho 2 H2G plus rho 1 H1G. Hope you got that. Now let's proceed further. So we just do everything the same, just the formula changes. When the question mentions vacuum pressure, you use this equation. When it just says pressure or gauge pressure, then use the other equation. P is equal to rho 2 G H2 minus rho 1 G H1. For this, you use equation P is equal to minus rho 2 G H2 plus rho 1 G H1 because it's just the opposite sign convention. That's it, nothing special. So that's it with our simple or YouTube manometer. Now we'll have a different type of manometer, that is differential manometer. So let's do with differential manometers. Okay. So differential manometers kind of look like this. There is one ball here. There is another ball at a different height, and it is connected by a YouTube manometer. That's it. Wait, I'll draw a little bit better. So this is connected by a tube, bro, kind of like this, whatever. And we'll do all our calculations based on this side, which was atmospheric pressure in the YouTube manometer. Now it will become another type of, like, what do you say, liquid pressure. So there will be like two liquids or one same liquid on both sides. And our formula will expand because there are two types now. So I will get to the formula in a little bit. I will kind of explain this a little bit more. So this one is A, other one is B. There is this liquid. Oh wait, I'll just do it. Do this one on the datum line and this one at a height h. So this will liquid, okay, and okay. So this, just like the other one, this distance we will be considering it as y, okay, because there are little more distances we have to consider, and this distance, which is the datum line, where both pressures are same, we will be considering it as h, okay, uh, and our distance from A here to our distance from this line. This one is x. Okay. So the formula goes like this. PA, pressure in A minus pressure in B is given as 1 second, guys. G into H rho G minus rho 1, where the rho G is the density of this liquid water, like this mercury, then density of heaviest liquid. Rho 1 means density of liquid at A. Rho 2 is density of liquid at B. I hope you got that. Now, that's it for this chapter, guys.